For your attention in the talks. So I was a bit like, yeah, Basil, uh, because we believe in CMake at TP. And we also find it's very cool technology. I think CMake is evolving very fast, and we are, and is also supporting a lot of older use case on the legacy and so on. And the C++ code base exists since multiple decades. So my talk today is about getting modern CMake technologies to get faster and safer build in C++. But basically safer build, you can get them by having faster build, faster test execution, faster compile time check, faster runtime checks. And so what we are doing at TP is basically enhancing the CMake experience. And also for people that don't like to write CMake or don't like to write build scripts, they can also get them generated out of the box. We're a small team, but we are growing. We're even an intern that is there that is not on the list, but we hope we can keep longer than expected. And we like a lot ISTs and build systems, so don't hesitate to talk to us if that's also in your interest. What my talk is about is that right now it's crazy about software safety, software security. C++, all the conferences I went the last year and this year, they are just speaking about safety. Be it people from Adobe, Sean Parent that coined a lot of safeties, definitions like in his talk at CppCon, but it also did one at C++ Now. GF Bastien, that is working on self-driving cars at Wuhan Technology, and that is in our advisory board. And Tim Dumler, that coined a lot of the different type of safety, and also spoke about how we could improve actually C++ to get it safer. And it's also pushed by this big marketing that the Rust people are doing. So I'm also risking my life. I think C++ can be safe. And I think we don't need to wait for the standard to evolve. It's good that standards evolve, but there is a lot of things that we can actually already do today. And for first to know what we are looking at today, what we are looking at today is what is safety basically. And in a programming language is basically different topics. And the things that are currently a lot discussed in the C++ space is type safety, memory safety, which is kind of divided in different category, like bound safety, checking that you don't iterate over the end of a vector or things like this. And there's a threat safety, but also things that are covered by undefined behavior, like arithmetic safety. Currently in C++, if you add, if you increment a number that is already at the max of what an integer can contain, is not going to be catched because it's an undefined behavior for performance reason and so on. And this is about arithmetic safety. And actually, I also think there is a missing thing, but nobody is speaking about right now in that space. They all are like, oh yeah, safety, cybersecurity is very important. 70% of the vulnerabilities come from memory safety issues, but what if your software supply chain is not clean, is not reproducible, is not traceable? And that's something that I think is part of how you bring safety to C++ and to build system in general. And the question is, why do we care? And why all these people do care is because actually the NSA reported that indeed there is 70% of the vulnerabilities that are due to memory safety topics, and that's on issues, and that's the reason why the US government is like pushing companies to use memory safe languages, which C++ is not considered, but I think it is. And there is also the European Union that is doing something similar. And if someone doesn't do like a lot of effort to guarantee the memory safety of his application, they could be liable for issues. And that's why people like Sean Parent at Adobe explain their concern, because basically if there is an issue in Photoshop and it lands at a memory safety issue in Photoshop that ends up being used as a vulnerability to attack a system, then it will be the fault of Adobe and not of the people that use the Photoshop, basically. And that's a big shift in responsibilities. And I think we should care about safety because cybersecurity, and safety in that regard is security, what the people are speaking about. But there is a thing, you cannot get functional safety if you don't have security. If you cannot guarantee that your system was not compromised, if your build tree is not modified maliciously or so, then you cannot say, oh yeah, my system is functionally safe because someone could hack it and make the car just run faster or brake when it should actually turn right or turn left when it should turn right. And I think it's kind of a nurturing thing. You cannot get functional safety without cybersecurity and vice versa. And actually, how to achieve this today in C++? I think it's possible. And I think there is a lot of tooling. The problem is with C++ is there is a lot of vendors, so tooling is not always on compiler developers and so on. So tooling is not always easy to install and to set up and to have running. So today I want to show how you can achieve that with CMake and have better safety in your C++ code every day. So basically, what I want to focus, because I don't have like a full 2 hours, and I think it's good if we take like 3 topics. It's like memory safety, which is a big one, arithmetic safety, like undefined behaviors and so, catching them, and software supply chain safety, like how you guarantee that the software you have is of the correct, comes from the correct sources, basically, and that you can reproduce it and verify what you have shipped to your users. So CMake can help you with memory safety, and we are going to look at this. So basically, there is a small GitHub project that some people did that is named Sanitizer CMake. And you can just include it basically in your CMake list. And it will allow you to run sanitizers from LLVM on your code base. So basically, if you have a Clang compiler at hand, it can run basically different tests on your code. And there is different kind of sanitizer. There is address sanitizer, undefined behavior sanitizers, thread sanitizer, and so on. The first is about memory safety. Is kind of working on all platform and checking if you dereference address that are pointing to things that were deleted and so on. Undefined behavior sanitizer is like checking like almost all undefined behavior that you can find. Like it needs to be run at runtime as well. So it includes a small runtime overhead. So you have to run it in your test. Some people also have that as in production because there is also hardware-based acceleration for it. And you can basically catch like actual undefined behavior on actual memory allocation problems. And you have also thread sanitizer that is checking that you are not like doing data races on accessing the same shared resources. And if you would like to use this sanitizer, basically the only thing you need to do once you have included this CMake module and you have it on your CMake module path, you can just say find package sanitizers, and then you can basically add to any of the target that you use to build the fact that sanitizer can be enabled for them. And the thing is, then we have it, right? It's great. Or do you think there is an issue with that? No? No hint? So basically, no, you cannot run all the sanitizer at the same time, which is kind of a painful thing. Like you cannot run address sanitizer in the same execution as you run undefined behavior sanitizer. So you have to run the same test execution twice so that you get the feedback. So you also need to run the build different times. You cannot build a binary that can do all this because it instruments the binary in different ways. So you end up needing to have different toolchain file in CMake to be able, or different build configuration to be able to set, okay, I want to sanitize undefined behavior now. In this other build, I want to sanitize memory. And in this other one, I want to sanitize threads. And this actually tends to increase the number of builds you have to do and number of test execution you have to do. And that's why I think faster builds and remote builds are the solution to it, because you can run all these tests in parallel if you have enough computing power for it. And this is basically what we are looking at with Hassan right now. So if we use this pretty example, like it's a use after free. We create a small array and we delete it. Just never do that. It's like this code is awful, and please use vector and don't do this kind of stuff. But it's just for the purpose of the example. And then we actually use lib format to print the value of the array that is bound to a runtime value. So it's not possible to check at compile time that this thing is wrong and so it needs to be checked at runtime to some extent. And if you will build this normally for your Mac, you could use CMake through the TP command line and say tipi.t macOS. And then you will just like get the library and the package cache and so on be pulled by TP. And then you will get the things built, and you will be able to run it. And you will not even notice that it has a bug. It's just saying, yeah, hello world, you are free to use after 0. It's building without optimization, so it's nicely printing a 0. If it will be built with optimization, you will get a segmentation fault or some very weird output. We're just happy of padding. So you actually, as a developer, you miss the fact that you are using a different value. But if you add to this command line -sanitize memory for the target, then it's going to use the toolchain file we saw before. And because I have added this CMake project, then when I run this, it rebuilds it for address sanitization. And I get a nice output about basically, hey, I detected you are doing a heap use after free, and you are basically this heap use after free is on line 7, and you can see the thing was deleted here, and it was allocated here, and you can basically navigate and see here is the problem that actually arose, and you also see from lib format the stuff that. Currently, where it dereferenced it, basically. So it's very easy to debug. And the same you can do to catch undefined behaviors, which are kind of one of the big source for bugs and things, because when you read code, you don't necessarily notice that. For example, if this value is being set as maximum what the int can contain, if we increment it by any numbers, it will overflow. And this is okay, this is undefined behavior. This is specified to be let to whatever the hardware wants to do. But the problem is you will never notice, and you might have a bug in your logic with that. And basically, if you want to catch that, you can run the same build, but this time, instead of saying sanitize memory, you say sanitize UB. And you get then instantly a report about your test running, and you see I have a runtime error, sign integer overflow, a very big number, +1 cannot be represented in type int in that regard. So basically get this feedback instantly when you are coding that you have this issue. And what is cool is actually you can get it while you are coding. If you run this same test like this, you get the output every time you change something. Like if I add a second time the line, it automatically rebuilds and rerun the test and so on. And because that might start to be AV, because you need to do memory safety, arithmetic safety checks, and all the other thread safety checks, and you probably have multiple platforms I try to build, you can actually use remote execution for CMake that is included in TP. And you can just, once you logged into TP website and you downloaded TP client, you can do TP connect, and then you can, instead of building locally, build remotely. And here I can run the same test simply remotely. It contacts your cloud, which is written in C++, and the client is written in C++ as well. There is some Rust in the caching part. And we actually create a remote machine there, and we build the code there, and we execute the test as well here. And we can also run it with monitoring mode, like every time you type something or so on, you get that feedback. So basically, you can also start to say, actually, I want everything all the time. I want Linux sanitize UB. I want a Windows build as well, and I want my special toolchain file and so on. And then when you run this, you will have the different things run in parallel. And then you can basically free your PC from all that overhead of running all these tests and all these checks, and you get basically instant feedback. So that was it, memory and arithmetic safety. Now, the last part is how do you get software supply chain, security or safety? I'm extra using safety here because people tend to say, oh, yeah, but safety, it's not security. Actually, it all is. It's just like very specific in every other instances. So how you get software supply chain safety? In my eyes, and I don't know how much you care about it. And I don't know if SBOM is a topic on your end. Who is software bill of material? Is someone interested in that? Or like there is one person, yeah, two. Like being able to trace which licenses, which dependency you have, and so on. But also, are people like interested in having like totally reproducible build? Can raise hands or? Okay, yeah, more reproducible builds on SBOMs, like half of the room, basically. That's very cool. So basically, you can get that in C++. And compiler have gotten always better at it. And there has been a lot of fixes to compiler to bring deterministic builds. And to actually provide supply chain safety, you need, on one end, to save the information which source were used to build that, but you also need to be able to verify if you take the same sources, rebuild it, see if you get exactly the same binary, the same checksum. So you can say, okay, what I have been running there outside is exactly the same thing that I've built the time I released it. And this is why you need hermetic build and deterministic builds. We basically have an issue in C++ with some macros on some other topic. I was very curious about the globbing topic on the Bazel thing. I hope it sorts the names of the file, because if it doesn't, the file order that will be fed to the compiler on linker will very likely be changed every other run, and so you don't have a reproducible build, because if you list a file folder on Linux, it will just be based on how Linux cached it, on how Linux accessed it, on how it was basically stored at the time it was modified, and so on. So this is a really big thing, and this is the reason why we force people to write in CMake. We say you should write the file yourself. You can also sort them instead of listing them all. The other thing is date and time macros. There are people that like to write in their build like, hey, it was built on this date and on this time, and be able to show that in their about window. But that makes the build a bit non-reproducible if you cannot change it. And there is some stuff also with link time optimization. It needs for some of the optimization randomness that generates duplicate symbols, so with random names, so that they can like inline better some stuff and so. And this needs to be addressed when you do a reproducible build. And the last one, and it seems like the most silly one, but it's not that easiest, is that you have a file macro, and a lot of log library and so use that, and they actually have the path prefix of your code, which basically is different on every other user that checked out your code, and when he builds it, he has a different result, and you have to be very careful on where you place things, where are your headers, and so on, if you want to be sure you have a reproducible build. So on MSVC, to get rid of the date and time thing, you have a hidden non-documented flag that is named brepro. It's very important to use that one because the portable executable format on Windows is also containing date information. For GCC and Clang, you can actually set the date. So for GCC, you can set it to my birthday. And then you're sure you always get the same date in your on time in the date and time macro. For Clang, you can just put it to 0. It's better anyway. Nobody cares of my birthday. Well, perhaps at some point we'll see. It's so sad. On the compiler randomness, this is something that is basically on GCC FLTO. It can be also on some linker configuration. But basically, what you can do is you can take the checksum of the file, because you still need to have something different for each file, and use that checksum to actually feed the random seed that the compiler would use for the optimization. So this provides one of the, like if the file didn't change, it's the same hash. If it changes, another one, and you can get FLT out of it. And now there is the last one, file, macro, and path prefixes. So MSVC, just don't update your machine. Just never install another Visual Studio version. Never check out in another place. There is just no way you get rid of the file prefixes. Neither in debug symbols, nor in the file injection that the preprocessor does. You can strip them at best by replacing all strings that look like a file path, but it's like very involved, and there is actually no help for that. On debug builds, you cannot guarantee reproducibility. And for Clang, there is not a solution for the file macro, but there's a solution for the prefix that the debug symbols involves. For GCC, you can just set whatever path you want to replace with another one, actually. To say I want to replace my home workspace, Damien, or Dominatreg, which is my nickname, by central build folder, for example. But you have to do it for all the paths you want to replace. So if you have a lot of library in the system, and so you have to do so. And the only actual sane solution I could provide, and we worked on at TP basically, it just build in the same environment at the same path all the time. Like it's the only way you actually get rid of that for all platforms. And to get that, and to get, in that case, safety with your build and being able to verify that your software is actually coming from your sources, you need to teach Ninja to know a bit more about your build files, and this is what we did, is actually merge Ninja on Git, on CMake together, so that you have a content addressable file system, so that you can track the changes that are done to sources, and you can relate the .o file to the source file at which version and so on. And you can also use Git to mirror your sources at a path that are invariant. So basically what we did is like using Git to mirror your sources in some place, and create some central build folder, and create binary cache packs of this build folder, so that you can have a connection between your build tree, your Git repository, and each build artifact mapped to each files in each of the Git commits that you had. And basically what we do is that we track each build snapshot by Git commit. And when you have this, you have Git, you have CMake, you have these cache packs, and you have cloud builds. We see it on the right, or like containerized and virtualized build. Then you can have really reproducible builds. You also need to have the flags I said before, but that you can get by default in some toolchain in TP. And so we solved the file problem. And I mean, it's not easy, but when you have it, it starts to be pretty cool. Because you can see when you change just one thing to your code, it's just adding some bytes to your binary and nothing else. And this works like this. We take your workspace, we clone it in some central location. On Windows, it's somewhere on the C drive. On Linux, it's in user local, actually. There's a small mistake on the slides here. Then for each of the Git commit that you build, we actually make a build snapshot out of it. And we use an advanced Z-stud compression with a correct layouting of files, so that we can actually pack them together in one big pack. And for example, for the LLVM project, we could compress 100 times 10 gigabytes of build trees in 100 megabytes, thanks to this. And then we upload that, and we redownload that on each of the CI machine, on each of the developer machines, whenever you want to build something that a colleague already built. Or if the colleague didn't build, but he built a previous commit, it will do an incremental build based on the previous commit, basically. So it's a bit different of what basal caching is doing, what was explained. Is more like when a build session is finished, we upload it based on the Git commit information, and then it can be reused, basically. And this is the way you get a fully reproducible build. And I think really that it's the way we get to safety in C++. Faster way to have checks, have them by default, have all cached, have all reproducible, and have the possibility to check the cache entries by redoing the build from the sources by using the metadata there. So remote CMake build, it's, I think, one of the things, and or caching and mirroring, and this is the other thing that makes it possible. But you need to be able to run this UBSAN, ASAN, and so on. And that's why I think the cloud can come handy. TP is free to use. You can also use it on your own hardware. There is a way to use some local runners. I would be very grateful if we get some feedback from you on that we can improve the product and the experience generally. It's just a click away. Shameless plug, right? You just sign in. GitLab support is being rolled out. Agonis has been working hard on it. And then you get on an onboarding wizard, and you just can install it on the command line wherever you want, and do TP connect, and then you can do remote build or local build if you don't want to use the cloud. Thank you very much for your attention, and I think the pizza should be there. I hope so. And we'll have drinks as well, so thanks.
Yes, so since you mentioned memory safety and reproducible builds, I'm not super deep into this, but I know on Linux, for example, if you build binaries, they have some mechanisms like stack canaries or address space layout randomization that are supposed to protect your binaries a bit and maybe introduce random elements into them. Doesn't that prevent you from having deterministic output?
The randomization happens at runtime. The resulting binary is being the same for the source file you build. If I understand that correctly, what you're saying is ASLR, right? The address space layout randomization. Yeah. This is something. The binary is always like kind of the same, sequential and so on, but every run is going to be randomized. Oh, okay, yeah. So that's not impacting like the build reproducibility or traceability. On the UBSAN and all this stuff will still work because they will work inside the process. Actually, UBSAN and ASAN, they actually add a library which replaces malloc with their own version and so on to actually check for things that you do. It's a bit like Valgrind as well. There's a lot you can catch also at compile time with that I didn't cover here, with the GSL, the guideline, the standard guideline library, and you can also use clunktidy and other tools to actually check them. And this you can also do like in monitor mode or so, running every time you do a change, you have this feedback. But yeah, at some point, if you want to catch everything, you have to run it, and I think it's very good you have that. Yeah. Sorry, I went a bit. I did an ellipsis. Thanks. Thanks. Oh, okay.
Hey, so because you run builds remotely, you need to have a kind of environment which mimics the local one. And for example, well, with local builds, this is not a problem, but basically forces you to kind of declare everything as an input, including the tools. So how do you handle this with TP? How do you handle remote environments that mimic the local one?
So the difference to what Bazel remote execution is doing, that scales horizontally on many machines, we go cloud first, and we say basically, we are going to take the biggest machine that you need for your build, that you can get in the cloud, and we are going to burst the build on it, and when you are done, we are gonna stop building. We have a limitation of whatever hardware is available in the cloud, but there are some nice 500 cores thingy. And we actually have some that makes it also possible to run things that you don't know all the input and output there. That's why we do this mirroring. So you get kind of a caching also for texts that are not yet ready to be cached or so on. But yeah, it's a different approach, and I think both are valid. And I think there is probably a good decision to be made by CI teams and developer teams following how much project they build, if they build always the same project and so on, what makes more sense in that regard, yeah. And does Glob sort the files?
Yes, it does. That was a good guess on your end, by the way.
Okay,
nice.
Because I would expect that from Bazel, yeah. Cool. Actually, CMake does it as well. In the meantime.